So everyone Manchi at home? Yeah, okay, very good, very good. I'm also okay, okay, no problem. I'm also good. So what's going at home? Chilling or studying? What's going on? Chilling or studying? Yeah, studying. Yeah, no time to chill, sir. We will do chilling, sir. Whole life is left to chill only. Yeah. But we will do chilling after NEET exam. Yeah. We will, if now we are doing chilling, that means we are doing chilling with study. Yeah. Otherwise, we will do complete chilling, complete chill life after 1st August. But till that time, we will work very hard. Yeah. Okay, no problem. Okay. And I think IPL is also going to start now. IPL is also going to start now. Oh, don't waste your time in IPL. If I find anyone is watching IPL matches, I will come to their house and I will beat them. I'll give punishment there. Yeah, yeah, okay, yeah, okay, no problem. Ugh. Okay, you can get information who won the match, who lost the match. Yeah, yeah, no, nothing matters. So many matches will be there. For time pass, people watch IPL. Yeah. So no one will watch IPL. Focus on your study. Just now, less than 4 months are left. 3.5 months are left. You are not realizing importance. Yeah. So much time. Yeah. So now time is coming very close. So give your 100% time to your studies. Yeah. Okay. No problem. Yeah. Now let's start with the class. Yeah. I don't know about from Monday online class will stop. I don't know about that. So come on, leave all those things. Okay. Now be focused. Understand. I think in last class we were talking about type of materials now. We studied about paramagnetic material. We studied about diamagnetic material. Yeah, and I told you diamagnetism is a universal property. Everyone remembered all these things? Yeah. Yeah, you tell me what is Xi for diamagnetic material? Xi for diamagnetic material. Xi for diamagnetic material. Negative. Yeah, less than 0 means negative, but not less than -1. Minimum value of Xi is -1. Acha, what is Xi of paramagnetic material? What is Xi of paramagnetic material? Small positive value. Yeah, very good. Small positive value. Oh, small positive value. Acha, who has more permeability? Diamagnetic material or paramagnetic material? Who has more permeability? Para has more permeability, Baba. Mu was greater than mu naught for para. For dia, mu is less than mu naught. Yeah, okay, no problem. So this is how we have talked about. Now today we'll be starting with our third type of material. You write ferromagnetic. Ferromagnetic. First, we will talk about what is ferromagnetic material. Then we'll talk about different things from here. Yeah. Ferromagnetic. So you write some point. You write these materials are actually magnet. These materials are actually magnet. These materials are actually magnets, but without external field. These materials are actually magnets, but without external field due to randomness. But without external field due to randomness, they don't have any magnetism. These materials are actually magnet, but without external field due to randomness, they don't have any magnetism. When external field is applied, they develop large amount of magnetism because they're magnet now. When external field is applied, they develop large amount of magnetism and suffer strong attraction So be focused, understand how we'll be talking about. Now change the paragraph and write the most important thing. You change the paragraph and write the most important statement. You write, ferromagnetism is explained with the help of Ferromagnetism is explained with the help of ferromagnetism is explained with the help of domain theory. There is one theory which explains this ferromagnetism. If question will be asked tomorrow in your NEET, they will ask you domain theory explain which property of the material, that is ferromagnetism. Always remember we explain ferromagnetism with the help of domain theory. I will tell you what is this domain theory. Okay, no problem. Be focused, understand how we'll be talking about. Yeah. So first thing, always remember ferromagnetic materials are actually magnets. Ferromagnetic materials are actually magnets. If you look at iron now, iron gets attracted by magnet. So always remember ferromagnetic materials are already magnet, but without field, that magnetic moment is random. So that's why they cancel. That's why they don't show any magnetic field. But when you apply external field, they develop huge amount of magnetism. If they develop huge amount of magnetism, they will suffer a strong attraction. And this whole thing is explained with the help of domain theory. So understand what is this domain theory, what this theory says. Just see here how we'll be talking about. Just see what this domain theory says. This domain theory says like this. For example, if you have any ferromagnetic material now, assume I'm having one piece of ferromagnetic material. And if you observe this ferromagnetic material at molecular level, what will happen in this ferromagnetic material? We will have domains. Domains means colonies. Domain word means colony. So what happened? What this domain theory says? In a ferromagnetic material, we have colonies of dipole moment. We have colonies. We have domains. It says like this. For example, if you see, there is one colony and every colony magnetic dipoles are there because actually they are magnet now. So in every colony magnetic dipoles will be there. But all these dipoles, all these colonies will be random. So due to their randomness, what happened? They cancel their magnetic moment and net magnetic moment is zero. These colonies which you are seeing, cluster which you are seeing now, these clusters are known as domain. Yeah, domain means colonies. So actually in ferromagnetic material, you have cluster of magnetic moments in different direction. So this domain, this colony, this domain, reverse. So they cancel each other. But when you apply external field now, when you apply H, external field H, intensity of magnetizing field or force H, all these domains come in one direction. All these domains which you are seeing there, all these domains will align in one direction. All these domains will come in one direction. They will come like this. They will come like this. All domain, all the colonies of dipole moment, all will come in one direction. And if you see, this is the structure for magnet. If you remember, all magnetic dipoles are. So what happened? This converts to ferromagnetic material, converts to a magnet. And its M now is not zero. It will behave as a magnet. It start behaving as a magnet. Behave as magnet. First to draw this, come on. Yeah. This is domain theory. In ferromagnetic material, we have clusters of dipole moments in random directions, which cancel each other. But when you apply external field H, all these domains, all these colonies come in one direction. Once they will come in one direction, it will convert to a magnet. So tell me, what is explanation for ferromagnetism? How we explain ferromagnetism? How we explain ferromagnetism? With the help of one theory. Come on, tell me the name of that theory which is used to explain ferromagnetism. Yeah, domain theory. This will be only asked. No one will ask you this diagram in your NEET exam. They will ask you the ferromagnetism of a body is explained with the help of domain theory. With the help of domain theory. Diamagnetism with the help of Lenz's law. Paramagnetism with the help of unpaired electrode, and ferromagnetism with the help of domain theory. Yeah, okay, no problem. Now understand how we'll be talking about. Yeah, and they will suffer, you tell me, they will suffer attraction or repulsion? They will suffer attraction or repulsion? not attraction, say strong attraction. Use field came there now, so they will suffer strong attraction, not attract. Smallest, less attraction is for para, and for ferro large attraction, strong attraction. Now understand how we'll be talking about. Now we'll be talking in the terms of xi. Just see here, I'll be simply saying that means, sir, if you are talking about ferro now, sir, for ferromagnetic material, sir, B net will be very, very large than B vacuum. Same thing we are doing in the last class also. Because here developed magnetic field is very used because it became magnet. So B net will be very used. That means B net will be very, very large in comparison to B of vacuum. That means mu of ferromagnetic material will be very, very large than mu naught. That means you can say mu means mu r into mu naught will be very, very large than mu naught. All these things we did in the last class also for different material. Now this mu naught will get cancelled. That means mu r will be very, very large in comparison to 1. That means from here we'll be saying, sir, mu r, if I want, I can write mu r as 1 plus xi will be very, very large in comparison to 1. Now this 1 will get cancelled. That means xi will be very, very large in comparison to 0. That means xi for ferromagnetic materials will be positive. C, very, very large than 0. And positive, and that positive value will be large, very large positive value. First you write this, come on. Same process which we did for different material yesterday, same thing I'm doing. Yeah. So who has positive xi? Who has positive xi? Who has positive xi? Who has positive xi? Yeah, both para and ferro have positive xi, but there is a difference between xi of para and ferro. What is that difference? What is that difference? Para also has positive, ferro also has positive. Yeah, para will have small positive, ferro will have large positive. Yeah, okay, very good. Yeah, who will have negative? Who will have negative? Yeah, dia will have negative. Acha, which medium will have maximum permeability now? Now you tell me which medium will have maximum permeability? Ferro. So always this is also mu of ferro is always greater than mu of para, is always greater than mu of dia. You can write this also. Yeah. Okay, very good. Now I will give you one question where I will give you some values of xi. This is a very famous type of question. You have to see the value of xi and you have to tell me which is paramagnetic, which is diamagnetic, which is ferromagnetic. So I will give you some values of xi and you have to identify the material. Okay, no problem. Everyone has writing done? Done, yeah, okay, no problem. Yeah, so see here, I will just give you some values of xi. You will just tell me, okay, no problem. And give me answer at once. All 5 values you will give me at once. Yeah, okay. Yeah, first 3 DPF. First one is diamagnetic, second one is paramagnetic, third one is ferromagnetic. Yeah. Yeah. Fourth one, -4. Yeah, first one is dia. I think everyone knows. I think everyone has understood. No problem in that. Sir, first one is diamagnetic. Second one positive but small positive paramagnetic. Sir, third one is positive but large positive ferromagnetic. Come on, tell me for fourth one. Do not exist, Papa. Don't say diamagnetic. I told you minimum value. Minimum value is -1. You cannot get less than this. So this is not possible. Not possible. No one can have xi less than -1. This is what I was telling you last class. And fifth one, xi equal to 0. Oh, vacuum. I think I told you. Xi equal to 0, vacuum. Yeah, okay, no problem. So this will be vacuum. Yeah. So this type of questions are asked. Okay, no problem. Yeah. This is a very famous type of question. They will give you different value of xi and they will ask you to identify the body. Okay, no problem. Now I'll move to some theoretical questions which are asked here. I will talk about some theoretical questions which will be asked here. Be 100% focused. I'm giving you time of 10 seconds. Come on, see all this situation. Revise all these things. I'll talk about one more very important situation. Two situations are very important which I'm going to talk here. Oh, once completed, you can say done. Arey, always. Oh, once I will say done, you can say you'll start saying done. Oh, not done. Who is saying not done? Yeah, okay, now be focused. Be focused, understand. Understand how we'll be talking about. Okay, now understand. Now understand. Acha, just now I told you. Now be focused, most important question. Just here how we'll be talking about. What I told you, ferromagnetic materials have maximum permeability. Diamagnetic materials have minimum permeability. You tell me what is meaning of permeability? What is meaning of word permeability? What is meaning of word permeability? You have studied about permeable membranes, semi-permeable, allowing. Permeability means allowing something to pass. Here we are talking about magnetic field, means allowing magnetic field lines to pass. Always look at the name. Permeability means it will allow to pass. So always remember, if permeability of a medium is high now, it allows maximum field lines to pass through it. That happens for ferromagnetic. You write. If a medium has high permeability, I told you that someday I will tell you meaning of permeability. You write. If a medium has high permeability, means it will allow maximum field lines. If a medium has high permeability, it will allow maximum field lines to pass through it. If a medium has high permeability, that means it will allow maximum field lines to pass through it, which happens for ferromagnetic. Which happens for ferromagnetic. Diamagnetic allow minimum feed lines. But this mu is less na. Less means permeability is less. Permeability means allowing. If permeability is less, it will allow less feed lines. You write diamagnetic materials allow minimum feed lines to pass. And I'm going to draw three different bodies. You have to see and you have to tell me which body is which quantity, which body is which material. I will draw some bodies. Three bodies I'm going to draw. You have to see these three bodies and you have to tell me which is para, which is ferro, which is dia. This is the first body. Okay, no problem. This is a second body. No problem. I think you know the answers. People started giving answer also. Yeah, you understood. Third body. Everyone wants to go through the third body. All field lines want to go. Tell me if this is A, this is B, this is C. You tell me which one is which. Oh, DPF. Yeah. Okay. Sir, this is not allowing field lines to go. Now you see field lines don't want to go through there. That means permeability is less. Who has less permeability? Dia. So, sir, this is diamagnetic. So, this is allowing field lines to go, but less. So, this is para. And this is allowing maximum field lines to go. So, this will be our ferro. Dia, para, ferro. चमकी बात. Everyone understood? Yeah, now I'll be moving towards one more theoretical question. 2-3 theoretical questions are there, otherwise no numericals will come from here. Types of material, what numerical will come? I'll move to one more theoretical question. You will see and you will tell me. Just here how we'll be talking about. So everyone has written, writing done, figure drawn, and draw nice diagrams like me. Don't draw chatta diagram. Yeah, you see how nice my diagrams are there. Yeah, okay, yeah, okay. So draw nice diagram. Okay, now be focused. Now be focused. Understand. One more theoretical question. Yeah, one more theoretical question. Yeah. Actually, what will happen in this question now? Ooh, yeah. Okay, now understand. What will happen in this question? In this question, they will give you one YouTube to watch video. They will give you one YouTube in which they will pour some liquid. They will say one YouTube is there, okay, no problem. And they will say you this YouTube is there, okay, no problem. And in this YouTube, they will put some liquid. For example, I'm putting liquid. So, you know, if you put the liquid on both arms, height of the liquid will be same. Liquid level will be same on the both arm. Understand how question will be asked. Now they will ask you to identify nature of the material. Understand nature of the liquid. Which liquid is this? Whether this liquid is diamagnetic or paramagnetic or ferromagnetic. So understand how we'll be talking about. You tell me, assume if this liquid is diamagnetic, and if you bring any magnet there, someone says, sir, if I bring one magnet to one of the arm of this YouTube, I put some magnet, I brought one magnet here. What will happen to the diamagnetic liquid? It will suffer repulsion. So due to repulsion, liquid will try to go away from magnet. It is suffering repulsion. It will say, no, I will try to go away. If it will try to go away, the arm where you will bring the magnet, their liquid level will fall. And in opposite arm, liquid level will rise. Repulsion is there na, diamagnetic material na, diamagnetic liquid. So what will happen? Liquid will suffer repulsion. Due to repulsion, what will liquid will try to go away from magnet. So here liquid level will fall, here it will rise. Now you tell me, if the same thing, same experiment I am doing, but in now this in YouTube, I am putting some paramagnetic or ferromagnetic liquid. What will happen if I now bring poles? Then what will happen? Bolo, what will happen? Come on. I will be saying, sir, if it is para or ferro, that liquid will suffer attraction, sir. If it is para or ferro, what will happen? More and more liquid will try due to attractive force of the magnet will pull the liquid towards itself. So what will happen? In the arm where you will bring the magnet, liquid level will rise. And in the other arm, liquid level will fall. Yeah, for ferro, rise will be more. Someone says for ferro, what will happen? Rise will be more. Because ferro will suffer more attraction. So rise will be more for ferro, less for para. But for both of them, it will be rise. You can draw this situation. Come on. Chamki baat. Everyone understood? Yeah, okay, very good. Yeah, okay. So you tell me, if liquid is diamagnetic, then label of liquid in the arm where magnet is brought will fall. Yeah, due to repulsion, it will fall. If it is para or ferro, attract rises. More rise for whom? Ferro. Why for ferro? Rise will be more. Strong attraction. So that's why. Okay, yeah. Okay, so this is how we can talk about. Okay, no problem. Now I'll talk about one more situation. Yeah. Okay, so this is how we are talking about. Now see one more last situation, which is very, very important. Yeah. Okay. Yeah. Okay. Understand one last situation from here. Be focused. Understand. And this is also very, very important. Acha, one question is asked like this. For example, assume I have a rod. This rod can be made up of paramagnetic material. It can be made up of diamagnetic material. It can be made up of ferromagnetic material. You can identify whether this rod is of diamagnetic or para or ferro. Understand how we'll be talking about. One question is asked. Just see here. As always remember, if this is a piece of rod, and if you put this piece of rod between the two poles of magnet now, that means if you put this piece of rod in the magnetic field, if this rod is made up of diamagnetic material now, assume here I am having north pole, here I am having south pole. Understand how we'll be talking about? Just see. Assume if I'm having two poles of magnet, north pole, south pole. I know sir, magnetic field lines will be like this. From north pole, magnetic field lines will go to south pole. Understand what I'm trying to tell? In this magnetic field, if you put, yeah, okay, understand. If assume here we have north pole, here we have south pole, and between north pole and south pole, if you put a rod, if this rod is made up of if this rod is made up of diamagnetic now, what will happen to the rod? From both poles, it will suffer repulsion. From here, it will always come in equilibrium like this. Understand? What will happen? If this is made up of what happens to diamagnetic material? Diamagnetic material suffer repulsion. So this end will also suffer repulsion. This end. From here also repulsion will come. From here also repulsion will come. It will become perpendicular to the field. It will not go away. It is hanging there. What will happen? So always remember, you write this point. And always remember, if it is para or ferro now, it will suffer attraction. So it will come in the direction of field. Are dia suffer repulsion, so it will align perpendicular to field. Para and ferro suffers attraction, so it will align in the same direction of field. You write this point. Come on. You write. If a rod is hanged, between the two poles of magnet, if a rod is hanged between the two poles of magnet, then first you write, it will align perpendicular to the field. Then it will align perpendicular to the field, in bracket transverse. Perpendicular also means transverse. It will align perpendicular to the field, in bracket transverse. If, you tell me, if it is diamagnetic, because it will suffer repulsion from both sides now, so it will rotate to become perpendicular. If it is diamagnetic, yeah. Second you write, it will become parallel to field if it is para or ferro. It will become parallel to field if it is para or ferro. It will become parallel to field if it is para or ferro. Why dia becomes perpendicular? Why para and ferro becomes parallel? Why so? Sir, dia suffer repulsion now, so it will try to go maximum away from the poles. So that's why this side is close to this pole. Now it will try to move away from the pole. This will also try to move. So that's why it becomes perpendicular. But para and ferro suffers attraction. So it becomes parallel to the field. I'm giving you 10 seconds. Come on, see all these things. We'll move to the next part. These all three are very, very important. Tomorrow one guarantee is there. If theoretical question will be asked, it will be asked from these three questions. Now understand. Now we'll be moving towards one more part. Be focused, understand. Yeah, we'll be talking about one more part. Just here how we'll be talking about. We are going to talk about some small laws which will tell us dependency of magnetic susceptibility Xi on temperature. First thing, you tell me, if you increase the temperature, what will happen to the magnetism of the body? If you increase the temperature of the body, what will happen to magnetism? Increases or decreases? It decreases now. Or if you increase the temperature, randomness will increase. If randomness will increase, what will happen? If randomness is more, magnetism will be less. Yeah, domains may break. So understand this. Okay, so this is what we are going to study. You write Curie's law. Madam Curie's law. And understand each and every point. Theoretical questions will be asked. You write it is applicable only for paramagnetic material. This is the first question which is asked. Which of the following, for which of the following material we can use Curie's law? Only paramagnetic material. It is applicable only for paramagnetic material. Very, very important point. It is applicable only for paramagnetic material. You cannot apply for anything. You have to apply this Curie's law only for paramagnetic material. Next point you write. This is the statement of Curie's law. You write magnetic susceptibility Xi of a paramagnetic material. Magnetic susceptibility Xi of a paramagnetic material will be inversely proportional. This is what I was talking about. If you increase temperature, I will decrease, Xi will decrease. Magnetic susceptibility Xi of a paramagnetic material will be inversely proportional to absolute temperature. What is meaning of absolute temperature? What is meaning of will be inversely proportional to absolute temperature? Yeah, in Kelvin. In bracket you write Kelvin. Yeah, temperature. But this is the first mistake which students do. Xi of a paramagnetic material will be inversely proportional to absolute temperature in bracket Kelvin. That means temperature they will give in exam intentionally in Celsius. So you have to convert into Kelvin. Yeah. So Xi of a paramagnetic material will be inversely proportional to absolute temperature. Now understand how we'll be talking about. Small numericals can be also asked. So just see here what this say. Curie's law applicable only for para. So this says Xi of a paramagnetic material will be inversely proportional to absolute temperature. That is temperature must be in Kelvin. Okay, be focused. Now from here, when you remove proportionality, now you get one constant, and that constant is Curie's constant. If you remove proportionality, one constant will come, that is your Curie's constant. That means from here you can say, sir, Xi into T will be constant. If Xi into T is constant, that means Xi1 T1 means Xi at temperature T1, Xi1, Xi at temperature T2, that is Xi2. Xi1 T1 will be equal to Xi2 T2. And if you required, you know na, Xi will be also equal to I by H. So you can put this thing also here. So this will come I1 by H1 into T1. This will be equal to Xi2. You can write, depends on question, what they're asking you, I2 by H2 into T2. This is our Curie's law. And if you draw the graph of this Xi into T, xy equal to constant, it is coming like xy equal to constant. That means if you draw the graph of Xi and T, that will come a rectangular hyperbola like this. Yeah, okay. So first point, Curie's law is applicable only for paramagnetic material. Second point, Xi will be inversely proportional to temperature. That means Xi into T will be constant. Xi1 T1 will be equal to Xi2 T2. Xi1 is I1 by H1. So I1 by H1 into T1 will be equal to I2 by H2 into T2. But be careful, temperature must be always in. Temperature must be always in Kelvin. Absolute. Yeah, I'll give you one question. Come on. Simple questions are asked from here. You write. I will give you one previous year NEET question. You write, at a temperature of 27 degrees Celsius, at a temperature of 27 degrees Celsius, a paramagnetic material has xi equal to 0.4 at a temperature of 27 degrees Celsius, a paramagnetic material has xi equal to 0.4. Find xi at 127 degrees Celsius. Prashanti, correct. Very good. Very good. Very good. Yeah. Yeah. Okay. Very good. Very good. So many answers are coming. From boys, very less answers are coming. Come on. Yeah. Girls, you see, yes, very good. Harika, very good. Boys, only 2, 3 answers came. Come on. Rose, very good. Yeah. Okay. So I think everyone will get. Yeah. Girls are giving answer fastly than boys. Yeah. More intelligent. Yeah. Okay. Okay. Now be focused. I think everyone got. I think everyone knows, sir. We will use Curie's law, sir. Xi1 T1 will be equal to Xi2 T2, sir. So Xi1 is 0.4. T1 is given 27. This will be equal to Xi2. Xi2 you want, sir. T2 is given 127. Correct, Baba. This is Xi1 T1 equal to Xi2 T2. Oh, sorry. Okay, Baba. Okay, no problem. Yeah. Okay, okay, okay. Yeah, this is a mistake which students do. Yeah. So temperature you cannot take in Celsius. You have to take in Kelvin. So convert in Kelvin. I think everyone knows this will give us 300 and this will give us 400. So from here, if you calculate, I think everyone will get. So from here, if we calculate, we get Xi2 as 0.3. Everyone understood? Yeah. Okay, no problem. I'm giving you time of 30 seconds. Come on, see this Curie's law. For what type of material Curie's law is applicable? For what type of material Curie's law is applicable? Yeah, paramagnetic. Yeah, okay, no problem. While using Curie's law, temperature must be in Kelvin. Yeah, in Kelvin. Now you write the next. You write Curie's law. Curie-Weiss law. Actually, 2 scientists are there now. Curie-Weiss law. With the sound which you make in class as Curie-Weiss law. Yeah, I'm teaching in class. They are doing like this. When I'm saying Curie-Weiss law, they are saying Curie-Weiss law. That's a snake sound. Yeah. Okay. You write. Come on. You write. Yeah. Curie-Weiss law. It is applicable only for. It is applicable only for ferromagnetic material. Curie's law applicable for para and Curie-Weiss law is applicable only for ferromagnetic material. Okay. So Curie's law applicable for para, Curie-Weiss law is applicable for ferromagnetic material. So just see what is this? What is this Curie-Weiss law? Just see here, what is this Curie-Weiss law? Curie-Weiss law says like this. Xi of a ferromagnetic material will be proportional to 1 upon T minus Tc, where T is the temperature of the body and this Tc is known as Curie's temperature. The temperature above which Curie start dancing is known as Curie's temperature. This Tc is Curie's temperature. Temperature above which, I think you know Curie's temperature. The temperature above which Curie start dancing is Curie's temperature. Okay. 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 People are saying, no, sir, we know. Yeah. So Curie-Weiss law is applicable only for ferromagnetic material. First question which can be asked, for which type of material Curie-Weiss law is applicable? Ferromagnetic, first thing. Second thing is asked about definition of Curie's temperature. So we'll talk about Curie's temperature. You write this point, yeah. Ooh. Yeah, Acha, you tell me, be focused, understand. Okay, bring understanding, bring understanding. Okay, now understand. Acha, you tell me, if you increase temperature of a ferromagnetic material, what will happen to its magnetism? If temperature of ferromagnetic material is increased, what will happen to magnetism? Magnetism decreases. Arey baba, randomness increases. When you'll understand. Arey, this is the magnetism of ferro, very high, para very low. If you increase temperature of ferro, randomness increasing, magnetism decreasing, 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 decreasing. So a temperature comes where ferromagnetic material becomes same as paramagnetic, and that temperature is our Curie's temperature. You right? Come on. It is, yeah, you right. The temperature above which the temperature above which a ferromagnetic material, the temperature above which a ferromagnetic material starts behaving, the temperature above which a ferromagnetic material starts behaving as a paramagnetic, the temperature above which a ferromagnetic material starts behaving as a paramagnetic material is known as Curie's temperature. The temperature above which a ferromagnetic material behaves as a paramagnetic is known as Curie's temperature. Acha, you tell me, if you heat ferro, first thing you tell me, acha, if you heat ferro, what will happen? What it will convert? Ferro after heating will convert to, after some temperature, ferro will convert to para. If you continue heating para, what will happen? If you continue heating para, will it convert to dia? No, Baba, it cannot convert to dia. Dia is reverse property. You cannot reverse. You can decrease the property. Are ferro was more property. You can reduce it to less, but you cannot reverse it by heating. You write this point. You write, we can never obtain dia by heating para. Your paramagnetism will become less by heating, but it will never convert to dia. Right? We can never obtain dia by heating para. We can never obtain dia by heating para. Actually, magnetism of diamagnetic material in bracket Xi. Actually, magnetism of diamagnetic material in bracket Xi is independent of temperature. Always remember, Xi of diamagnetic material don't depend on temperature. Actually, magnetism of diamagnetic material in bracket Xi is independent of temperature. They have nothing to do with temperature. Temperature may bring change for ferro, may bring change for para. For dia, nothing change, no change. I'm giving you time of 30 seconds. Revise from the beginning. First, I will ask you some question, theoretical part going on. So everyone must revise all these things. Come on. I don't know whether they will stop online classes. I don't know. Some people are worried. I don't know. But some people are already having online batch now. They will not stop, I think. I don't know exactly. If they are asking you to come to the campus, you can come. No problem. Because anyhow, you have to come now. MPL stopped. MPL stopped because previously it was not there. Yeah. Ooh. So, first thing you tell me, come on. Ooh. No, online, offline, same syllabus. Nothing change. Yeah. You tell me, come on, you tell me. Okay, no problem. First thing you tell me. Okay. Acha, for which type of material Curie's law is applicable? Curie law is applicable for para. Okay, okay. Acha, Curie-Weiss law is applicable for Curie-Weiss law is applicable for ferro. Okay, no problem. You tell me, if you start hitting ferro, it will convert to para. Above which temperature ferro converts to para? What is the name of that temperature? Curie's temperature, TC, Curie's temperature. Acha, tell me, if you continue heating para, will it convert to dia? No, it will never convert to dia. How magnetic, how xi of dia depends on temperature? How xi of dia depends on temperature? Independent. Nothing, no dependency. Yeah. Okay, no problem. This is how we have talked about. Now we'll be moving towards our next part. We are going to talk about one more part. Understand? You write. Artificial magnet. Here we will study one curve, hysteresis curve. Here we will study about retentivity. Here we will study about corrosivity. Again, important theoretical part for your NEET exam. Artificial magnet. So understand how we'll be talking about. Be focused. Just see here. Yeah. First thing, always remember, natural source of magnet is very limited. Natural source of, it's not like that at your home you go in one playground, there dig the ground, you'll find one natural magnet. It's impossible. Natural source of magnet is very, very limited. But we require magnet everywhere now. Every device has magnet. The mobile phone that you use, the fan that you use, the AC that everyone has magnet. So we must know how to generate the magnet. And for that only we talk about artificial magnet. So that's, I will tell you how to generate a magnet. Be focused, understand. Just see here. So always remember. Acha, you tell me, which type of material will be used for artificial magnet? Shall I use diamagnetic, para, or ferro? Which material I should use for? Ferro. Because I told you, ferros are actually magnet. This is the definition of ferro. You write. Yeah. For artificial magnet, we always select ferromagnetic material. For artificial magnet, we always select ferromagnetic material. And always remember, we have two types of artificial magnet. One is our temporary magnet, which is also known as electromagnet. They will ask you questions for electromagnet. This is the important part. Temporary magnet or electromagnet. And second is our permanent magnet. Permanent magnet means the magnet whose magnetism is for small time, that is temporary magnet. The magnet for which magnetism is for longer time, that is known as our permanent magnet. And always remember, for temporary magnet we use soft iron. So for temporary magnet, this is, you have to keep this thing in your mind, we use soft iron. And for permanent magnet we use hard iron. Hard iron means steel. Soft iron is very soft. You can put as pillow. Is it like that? Soft iron is very soft. You can use it as a pillow. You can sleep. You can make bed of soft iron. No, soft iron is naturally occurring iron. Yeah, name is soft. You know, now if you mix some carbon in the iron, then it converts to steel. Now you have studied in metallurgy. Now some impurities added in the soft iron is actually naturally occurring iron. So one magnet will be temporary magnet, that is also known as electromagnet. It is designed with the help of soft iron. One is permanent magnet, depending on our requirement. Sometimes we want permanent magnetism, sometimes we want temporary magnetism. So for temporary magnetism, that is electromagnet, we require soft iron. For permanent magnet, we require hard iron. Hard iron means steel. The glass which you use for drinking water, steel glass, you can use that for making permanent magnet. Chamki baat, everyone understood? Yeah, now understand, be focused. Be focused, understand the most important part which I am going to tell you here. Now you'll be thinking, sir, what property a ferromagnetic material will have to use it for temporary magnet? We'll be thinking, na sir, why only soft magnet is used for temporary magnet? What is present in the soft magnet that is used for temporary magnet? Sir, what is present in hard iron? What is present in steel that we use it for? What is the reason, sir? Why? What criteria? What are the criteria which will decide that the way you give NEET examiner, some criteria are there, then only you can give the NEET in the same manner. So what are the criteria a ferromagnetic material must have to use it for temporary magnet, to use it for permanent magnet? And this criteria, this property we study with the help of a curve. That curve is known as hysteresis curve, and that curve is only designed for ferromagnetic material. You write hysteresis curve. Hysteresis curve. Hysteresis curve. I don't know the spelling. So first thing you tell me, for which type of material this hysteresis curve is designed? Can you draw for para? Can you draw for dia? Only ferro. Hysteresis is property of only ferromagnetic material. You write, this curve is designed only for ferromagnetic materials. This curve is designed only for ferromagnetic material. This curve is designed only for ferromagnetic material. Now see the curve. I will tell you how this curve is designed. So be focused, understand how we'll be talking about. Just see here, yeah. So you may have observed one stylish curve is there now. Yeah, all the curve in physics are not stylish. Some is a straight line, some parabola. This curve is very stylish. Some wavy nature will be there. Have you observed that curve? Stylish curve will come. It is like this. Yeah, like, yeah, okay. So understand, sir. Yeah, okay. Be focused, understand. Okay. Yeah, like leaf. Leaf means curvy structure. Okay, understand. Who is saying as you, sir? Oh, that is also correct. Okay, now be focused, understand. Yeah, okay, understand, bring understanding. Acha, always remember, every curve is designed with the help of two axes. Two axes means two quantities. Can you tell me this hysteresis curve is drawn for which two axes? X axis represent what? Y axis represent what? Yeah, understand how we'll be talking about. Yeah, okay, yeah. Okay, yeah, some people are giving, yeah, okay, yeah, very good, yeah, understand. Always remember, okay, actually what we are doing now, we are trying to magnetize a ferromagnetic material. What I am trying to do, I am trying to convert into magnet now. That means for converting a ferromagnetic material into magnet, you need external field. External field means H, and after H, body will develop I. So always remember, your hysteresis curve is always drawn between H, external field, intensity of magnetizing field or force, and due to this H, body develops magnetization I. Understand? You want to convert a ferromagnetic material into magnet now, that means you require external field. So one quantity will be H, which will be applied on the ferromagnetic material, and due to external field H, it will develop magnetism I. So hysteresis curve is always drawn between H and I, that is intensity of magnetizing field or force, and this intensity of magnetization. Now understand how I will start. This here. What we say? Achha, tell me, right now assume we are starting from 0. Right now H is also 0, I is also 0. You tell me, if I increase external field, what will happen to magnetization in the body? If you increase H, what will happen to I? Yeah, I will increase, obviously, sir. If you increase external field, sir, magnetization in the body will slowly increase. So what happens when we increase H now? I increases, and I attains one maximum value, that is saturation magnetization. That is maximum magnetic. Everything will have maximum value in a saturation. Your I will get maximum value. That is saturated magnetization. Saturated magnetization. Okay, keep on understanding. Keep on understanding. Okay, no problem. Be focused. Just see here. Yeah. So if you increase H, I will increase. I will increase. I will attain one maximum value. Saturated value. Now you tell me after this, if you decrease H, what will happen to I? If you decrease H, I should decrease now. But always remember what we feel. We feel that if I is increasing like this now, when H is increasing, when we are decreasing H, I should also decrease in the same manner. That is what don't happen. Always remember, if you are increasing H, I will increase. If you are decreasing H, I will decrease. But that increase and decrease will be not in the similar manner. If you are increasing H, I is increasing. If you decrease H now, I will decrease, but it will decrease less. It will decrease less. It will decrease less. And even when H will be 0, even when H will be 0, you see here, even in H is 0 now, body will have some magnetism. This is known as retentivity. Even if you remove at this particular point, what is your H? H is 0, but body will have some magnetism. This magnetism is known as retentivity. Even if you make external field 0, body will retain some magnetism. That is our retentivity. If you want to destroy this magnetism, you have to now apply field in opposite direction. Someone said, sir, if I apply field in opposite direction, obviously this magnetization will reduce. So for a particular value of H, what will happen? Your magnetization in the body will become 0. If you continue increasing your H in the opposite direction, now what will happen? Your magnetization will start in opposite direction. Again, it will attain saturation, and again, same thing will be followed. This is your hysteresis curve. First, you draw this. You can see stylish curve. It's like this. Yeah, wow. Oh, yeah. Oh. Artist. Oh, what is Pammu? Who's saying Pammu? Acha, Pammu means snake. Kappa means frog. I also know. Okay. Kappa means frog. Pammu means. Okay. Acha, one more word was there. I forgot. Tortoise, some word was there for tortoise. Tabelu, yeah, tabelu. Yeah, now I will use from tomorrow's class. Tabelu, yeah, tabelu now. Yeah, okay, yeah. Now be focused, understand. Okay, now understand. Okay. Now just see here. So what I'm saying, again, I will tell you, be focused. What happens when you increase H now? I increases, becomes maximum. But when you decrease H now, I don't decreases in the same manner. The way it increased, it don't decreases in the same manner. So even when you make it decreases less, so even if you make H 0 now, body retains some magnetism. That is known as retentivity. This quantity which you are saying, for example, if this is O, this is A, this is B. So this distance, this value of I which you are seeing here, this value OA is the value of I. This value of I is known as retentivity. Even when no external field is there, body has developed some itself magnetism. That is your retentivity. And this value, if you want to destroy retentivity, you have to apply field in opposite direction. You have to apply field in opposite direction. That is your OB. OB is the value of H. This value of H is known as corrosivity. And you write this point. Just we will explain this hysteresis curve in 2-3 lines. You write. Initially, when H is increased, I increases. Initially, when H is increased, I increases and attains maximum value. Initially, when H is increased, I increases and attains maximum value. But when H is decreased, it is found that But when H is decreased, it is found that I decreases, but by a lesser amount. I decreases, but by a lesser amount. So even when H becomes zero, body retains some magnetism. So even when H becomes zero, body retains some magnetism. This is retentivity. Look at the name, retain. This is retentivity. You write, change the paragraph and you write, in order to destroy retentivity, we have to apply field. In order to destroy retentivity, we have to apply field in opposite direction. We have to apply field in opposite direction. This value of H is coercivity. This value of H is coercivity. This value of H is coercivity. Now you tell me from hysteresis curve. I told you that this hysteresis curve is used to know whether the material will be used for it will be used for temporary magnet or permanent magnet. You tell me permanent magnet means it should permanently retain magnetism now. It should permanently have large magnetism now. So always remember, for permanent magnet, always remember these are the properties that we get for permanent magnet. You must always have. Can you tell me about retentivity and coercivity? Yeah, it must have high permanent. It permanently want to become magnet. So retentivity will be high. And if retentivity will be high, coercivity will automatically be high. So always remember, for permanent magnet, you must always have high retentivity and high coercivity. And for temporary magnet, yeah. So for permanent magnet, you must always, yeah. So yeah, okay. Spelling may be different. Spelling may be wrong. Don't worry about that. Yeah. So for permanent magnet, you must have high retentivity, high coercivity. And second, you tell me for temporary magnet. Come on, tell me for temporary magnet. For temporary magnet, both should be low. You want it to behave as magnet for small time, so it should not retain the magnetism. So it must have low retentivity and low coercivity. So this is the most important thing which we get from hysteresis curve. For permanent magnet, your retentivity, coercivity, both must be high. Permanently you want to make anything magnet now, That means it should retain very huge magnetism every time. So that's why retentivity is high. If retentivity high, corrosivity will automatically become high, because corrosivity is the field to destroy retentivity. So high retentivity, high corrosivity. For temporary magnet, come on, tell me. Temporary nah. Yeah. It should not retain more. It should so for temporary magnet, low retentivity, low corrosivity. Everyone understood? Yeah, come on, tell me for permanent magnet. For permanent magnet, come on. Pandit Varga, for permanent magnet, what is the property? High retentivity, high corrosivity. High retentivity, high corrosivity. Temporary magnet, low retentivity, low corrosivity. Now you tell me, yeah, for temporary magnet, low retentivity, low corrosivity. Now be focused, understand, yeah. This is one thing that we get from hysteresis curve. Acha, can you tell me what will be nature of hysteresis curve? Understand what I'm trying to tell. Be focused, understand. Yeah, okay, no problem. Understand. Always remember one thing. Always remember one thing. For permanent magnet, what is happening now? Yeah, for permanent magnet, what is happening? Your retentivity and corrosivity both are high. So when you draw the hysteresis curve for permanent magnet, now someone draws hysteresis curve for permanent magnet. If you draw the curve, what will happen? Retentivity high, corrosivity high. Corrosivity high means its width will be more. Corrosivity is deciding width of the curve. So understand, if your corrosivity is high, if I'm talking about high retentivity, high corrosivity, what will happen? Your hysteresis curve will be, hysteresis curve will be like this. You can see it. Retentivity high, corrosivity high. That means your curve, your hysteresis curve for this is the hysteresis curve for permanent magnet. That means this curve will be tall and wide. Arey baba, corrosivity is high na, width is more na. It will be tall and wide. Yeah, it like fat man. Like your vice principal, Prakash Garu. But he is very fat. I'm not talking about very fat. Tall and wide. Like Narendra sir, better. Permanent magnet, you see, retentivity high na, corrosivity high na. So that's why its curve, hysteresis curve seems to be very bad. I will again draw it. Okay, I did not saw it. Yeah, it's like this. High. It should be stylish. Okay, so stylish, it will go like this, something like this. Tall and wide. Yeah. Yeah, okay. Okay. So for permanent magnet, always remember, for permanent magnet, your hysteresis curve will be tall and wide. And now you tell me, for temporary magnet, how should be your hysteresis curve? For temporary magnet, what should be your hysteresis curve? Low retentivity, low corrosivity. Come on, tell me, what should be hysteresis curve? First, width will be not there. If width is not there, narrow. If width is not there, narrow. What about height? No, always remember there is one concept here where people make mistake. Be focused, understand. Yeah, always remember, for temporary magnet, what is student think now? High retentivity, high corrosivity, tall, wide. So student think here, low retentivity, low corrosivity. So short, narrow. For width, opposite narrow. For tall, opposite short. But that is wrong. Always remember, for temporary magnet also, hysteresis curve will be always tall and narrow. Don't think short and narrow. It will be tall and narrow. For temporary magnet also, your hysteresis curve must be tall and narrow. Yeah, like me. I'm tall, 6 feet 4 inch, and I'm narrow also. So like me. That is like Naren sir, that is like me. Oh. Yeah. Okay. Okay. Oh. Yeah. Do you think it is, sir? Why it's like that, sir? Tall and narrow, sir. It should be short and narrow now. Low, sir. High retentivity, high corrosivity, tall, wide. So low retentivity, low corrosivity should be short and narrow. Why it is tall and narrow? Be focus here now. Why it is tall and narrow here? Always remember, be focused here. Okay, now actually what happens now, always remember, height of your curve is not decided by retentivity is not deciding height of the curve is decided by saturation magnetization. Height of the curve will be decided by saturation magnetization which body gets, and magnetization will be always very high because you are using ferromagnetic material now. Understand what I'm trying to tell? Students think that high retentivity, high corrosivity, low retentivity, low corrosivity, they are tall, narrow. So here it should be, they are tall, wide. So here it should be short, narrow. No, tallness will be always there because tallness is not coming due to this retentivity. Tallness is coming due to magnetization, saturation magnetization. And saturation magnetization will be always very high because we are using ferromagnetic material now. So when you draw the hysteresis curve for temporary magnet, this curve comes like this. Just see, I will draw it. Just see. Low retentivity, low corrosivity, but magnetization will be high na. You are using ferromagnetic material na, magnetization will be very high. So tallness will be there. This curve comes like this. Tall, narrow. This is hysteresis curve for temporary magnet. In bracket, AKD, sir. My height is 6 feet 4 inch. Pansar, no. Pansar will not. Pansar is short also and wide also. Short and wide, if that example would have been there. Short and wide. Narendra sir height is slightly greater than me. Taufik sir. Okay. Okay, come on. I'm giving you time of 30 seconds. Come on. Yeah, I'm giving you time of 30 seconds. Come on, revise this hysteresis curve. Acha, one more last thing. Acha, tell me, always remember every curve tells, area of every curve tells you something. Always remember, yeah. Okay, still something else we have to talk about. Always remember, area of every curve represents something. So here also area of hysteresis curve which you draw now, this is also important theoretical question. Always remember this area of hysteresis curve represents loss in magnetic energy. And actually that loss will be, you write this point, area of hysteresis curve represents loss in energy. Area of hysteresis curve represent loss in energy. Area of hysteresis curve represents loss in energy, which is converted to heat. So this is also famous question which is asked, what the area of hysteresis curve represent? So loss in energy which is converted finally to heat. You see boys how good they are. They are saying, sir, your height is not 6.4, sir. It's 6.5. Good. You see, girls, you are not believing. You see, boys are saying there, sir, your height is more than 6. Okay. You see, boys, so nice people. They are saying, sir, your height is more than, yeah. Okay. Okay. Now girls are saying 7 feet. Don't make me tallest person in the universe. Okay, no problem. Okay. So this is how we have talked about. I'm giving you 10 seconds. Just have a look. Just have a look about all these things. I will ask some questions. What is buddhi? Yeah, equal to pravasa. Yeah, correct. They are also saying same thing. If you say me buddhi, I will say battatala. Okay, now be focused. Be focused. Understand? Acha, okay. No problem. First thing you tell me. What? Tell me about retentivity and corrosivity. Tell me about retentivity and corrosivity for permanent magnet. For permanent magnet, come on. Permanent magnet, high retentivity, high corrosivity. For temporary magnet, low retentivity, low corrosivity. Come on, tell me the nature of hysteresis curve. Tell me hysteresis curve for permanent magnet. Tall and wide. Yeah, tall and wide. Tell me hysteresis curve for temporary magnet. Tall and narrow. Tall and narrow. Yeah, okay, no problem. What is the area of hysteresis curve? Yeah, AKD, sir. Okay, very good. Achilles, sir. Very good. Yeah, good girl. Yeah. What is area of hysteresis curve? Loss in energy. Loss in energy. Now you write, come on, you write. Gauss law in magnetism. Just 2 minutes. Gauss law in magnetism. Gauss law in magnetism. Yeah, 2 minutes are left. We'll complete in 2 minutes. Understand how we'll be talking about what is Gauss law in magnetism, same as electrostatic. So be focused, understand what we studied. We studied about Gauss law in electrostatic. Now there I used to say E dot S will be equal to Q net enclosed by epsilon naught. This is our Gauss law in electrostatic. You know, in magnetism, in place of 1 by epsilon naught, we write mu naught. There 1 by 4 pi epsilon naught. Here we write mu naught by 4 pi. Yeah. And in place of charge, we talk about pole strength. So what we say in Gauss law in magnetism says like this: B dot S, magnetic flux. This B dot S is your magnetic flux. Magnetic flux associated through a closed surface. B dot S will be equal to M net enclosed into epsilon into mu naught, because in place of epsilon naught we use mu naught now. So mu naught into M net enclosed. But always remember, you know, isolated poles never exist. So M net enclosed will be always 0 na. Are net monopoles don't exist. So always remember, whatever the surface, whenever you tell me this is possible, can I have a closed surface in which only north pole is there? Is it possible? No, north pole and south pole will be always together. So that's why plus M minus M. So M net will be always 0. So that's why net magnetic flux through every closed surface, since M net is 0, it will be 0. You write this, then you write the last point. Yeah. You write. Magnetic flux associated through any closed surface will be always 0. Magnetic flux associated through any closed surface. Magnetic flux associated through any closed surface will be always 0. So this is how we have talked about all these things. This is how we have completed all these things. More situations from here we'll be talking next class. STC. Okay, bye, tata. Okay, bye. Do the questions of material. Okay, bye.